All right, welcome to The Explainer. Today, we're doing something pretty wild. We're opening up the official rulebook for the universe itself. We're diving into Chapter 4 of R. Shanker's classic, Principles of Quantum Mechanics, to break down the fundamental rules, the postulates, that govern reality at its very smallest, weirdest scales. Okay, so to really get a grip on these new rules, you gotta start with this kind of surprising fact. Our understanding of physics, for centuries, was incredibly successful, but it was also fundamentally incomplete. Turns out the universe is basically playing two different games with two completely different sets of rules. So, on one side, you've got the classical world. Think of a baseball. With Newton's laws, we can predict its path perfectly. Its speed, where it's going to land, the whole deal. It's certain, it's predictable. But those exact same laws, the ones that can chart a planet's orbit, they fail, and I mean spectacularly, when you try to apply them to a single electron. For that, you need the quantum rules, which are all about probability. And let's be honest, a whole lot of weirdness. And this isn't just theory. The old rules really started to fall apart with experiments like the famous double slit test. When scientists shot single electrons at a screen with two little slits, they didn't act like tiny baseballs. They acted like waves. They created this interference pattern as if each electron went through both slits at the same time. How does that even work, right? This wave-particle duality proved the old rulebook was toast. We needed a whole new way of thinking. So what exactly are these new rules? Well, here's our game plan. First, we're going to tackle what a quantum state even is. Then, we'll see what happens when we dare to look at it. After that, we'll check out how it evolves when we're not looking. And finally, we'll pull it all together into the complete quantum playbook. All right, let's jump right into postulate number 1, which completely redefines what it even means for a particle to exist. And it turns out, in this bizarre quantum world, asking, hey, where is that thing? That's not even the right question to start with. See, in our everyday classical world, a thing state is super simple. It has a specific position, a specific momentum. But this is where everything changes. In the quantum world, the state is described by this thing called a state vector. You'll see it written as psi. So don't think of it as telling you where the particle is. Think of it as a complete list of everywhere it could be, holding the probabilities for all possible outcomes, all at once. And this state vector, it's not pointing north or up or down. No, it lives in this huge, abstract mathematical world called Hilbert space. The best way to picture it is like an arena, a space of possibilities for the particle. And that state vector is just a pointer somewhere in that arena. And this, of course, leads us to one of the most famous, most mind-bending ideas in all of physics, superposition. What it means is a particle isn't just here or there. Nope, it's in this weird, fuzzy mix of all the places it could be, all at the same time. And that all changes the second we look. Which naturally brings us to the next postulate. And honestly, this might be the strangest rule of them all. What happens the moment we try to measure something? Classically, if you check the speed of a car, you're just finding out something that was already true. It's totally passive. But down in the quantum world? Oh no. Measurement is an active, almost violent event. The very act of observing forces the system to drop its fuzzy possibilities and choose one single state. You're not just observing reality. Your observation is what creates it. So how does this actually work? Well, postulate 3 gives us a clear-cut recipe. Step 1, you have to ask your question, like, what's the energy? In the language of math. They call this an operator. Step 2, the math spits out the only possible answers you can get. These are called eigenvalues, and you can't get anything in between. It's only these specific values. Step 3, you use that state vector we talked about to figure out the odds of getting each answer. And then step 4, the instant you measure, bam, the system is forced to pick one, and the whole state collapses into that single result. So just imagine, before you look, you've got this state vector, psi, just hanging out in that abstract space of possibilities. It's this beautiful, shimmering superposition of everything that could happen. At that moment, the particle literally has no single position. It has no single momentum. It's just potential. But then you measure it, and in that instant, that vector just snaps, collapses, onto one of the specific axes in that space, locking into one single concrete answer. The superposition is gone, and out of that fog of probability, a single, definite reality just pops into existence. And this is the absolute key takeaway, and it's a direct quote from Shankar. A quantum measurement doesn't tell you what the system was up to. No, it fundamentally changes the system, and it only tells you what that system is doing in the instant after you measured it. It basically resets the clock for the immediate future. Okay, but this brings up a huge question, right? If the act of looking is so dramatic and disruptive, what's happening when nobody's looking? How does a quantum system evolve on its own? Well, that's what our next postulate is all about. And this is where the legendary Schrödinger equation comes into play. What it says is that between measurements, when it's left alone, that state vector evolves perfectly smoothly. It's continuous, and believe it or not, it's totally deterministic. Yeah, it's just as predictable as a planet going around the sun. And this creates this wild duality at the heart of quantum mechanics. You have this graceful, predictable evolution of probabilities, and then bam! A sudden, random collapse into one reality the moment you interact with it. All right, let's put all the pieces together. Let's recap the totally new rules for reality we've just laid out. This is the quantum playbook. So at the end of the day, the game has completely changed. We now know things can be in many states at once. That's superposition. We've learned we can never be certain about an outcome. We can only talk about the odds. That's probability. And we know that the simple act of looking forces reality to pick a side. That's collapse. And of course, all of this leads to other famous ideas like wave-particle duality and the uncertainty principle, which basically says you can't know everything perfectly all at once. So you might be thinking, okay, this is weird, but why does it matter? Well, get this. These totally bizarre, counterintuitive rules aren't just for textbooks. They are the absolute bedrock of over 30% of the world's economy. I mean, the transistor in your phone, in your computer, that's a pure quantum device. It only works because we can control the wave-like nature of electrons. Without these rules, forget it. No lasers, no MRI machines, pretty much no digital world as we know it. When you boil it all down, the entire theory is this massive shift away from the comfortable, certain world we thought we lived in to a world built on structured, calculable probabilities. Like Shankar says, the theory doesn't tell you what you will get, it just tells you the odds for the only things you can get. And that leaves us with one last, really profound thought to chew on. I mean, the world around us feels so solid, right? It feels real, predictable, but we've just seen that the fundamental rules that build all of this, they're all based on chance, probability, and the act of us just looking at it. So what does that really say about the solid reality we think we experience every day?